Welcome to AI Frontiers. Today we explore the vision revolution through 112 computer vision papers published on October 16, 2025. This snapshot reveals breakthrough research spanning medical diagnosis to three-dimensional world generation, showcasing machines that are learning to truly understand what they see. Our journey through computer vision begins with a field overview, tracing the evolution from basic pattern matching to true understanding. We'll examine dominant research themes across all 112 papers, highlight key breakthroughs in medical AI and three-dimensional generation, and explore future directions shaping the next AI revolution. Computer vision has evolved significantly from its origins in basic pattern recognition. Deep learning enabled superhuman accuracy in specific visual tasks, but current research focuses on bridging perception with true understanding. The field is moving from isolated vision systems to integrated multimodal systems that connect seeing with reasoning and interaction. The first major theme emerging from these papers is multimodal and embodied understanding. Research like XModBench by Wang and colleagues tests cross-modal reasoning across vision, text, and audio. QDepth VLA by Li and colleagues enables spatial navigation capabilities, while UrbanVerse by Liu and colleagues creates interactive environments. Vision is becoming an active process rather than passive observation. Theme 2 focuses on advanced generation and controllable synthesis, moving beyond simple text to image conversion. TGT by Zhang and colleagues enables precise camera control in generated videos. OmniMotion by Li and colleagues generates realistic human movement respecting physical constraints. Terra by Huang and colleagues creates explorable three-dimensional worlds, while GDGen by Li and colleagues adds interactive physics to generation. The third theme addresses efficiency, scaling, and data curation to make powerful vision accessible. Mobius by Sagan and colleagues compresses models for mobile devices, while Fracat by Moriale and colleagues designs efficient architectures. Wang and colleagues create multimodal data quality classifiers, reducing reliance on expensive human annotation and enabling broader deployment. Several key findings represent revolutionary insights that change fundamental assumptions. Scaling AI with alternative supervision, as demonstrated by Chen and colleagues, shows models can learn from abundant weak supervision rather than perfect annotations. Native multimodal models eliminate modality conflicts, while structured visual reasoning improves understanding. Three-dimensional native thinking enables consistent world modeling. Methodologically, several approaches serve as technical workhorses across these papers. Diffusion models dominate generation tasks despite computational intensity. Multiple instance learning handles large medical images by analyzing patches then aggregating information. Parameter-efficient fine-tuning with LoRa adapts large models efficiently, while synthetic data generation overcomes data scarcity challenges. A selected paper demonstrating medical AI breakthrough is scaling artificial intelligence for multi-tumor early detection, with more reports, fewer masks by Bassi and colleagues. This research uses radiology reports instead of manual tumor masks for training, achieving expert-level performance with 101,000 reports. The approach detects tumors in organs with no previous segmentation models, potentially democratizing cancer detection globally. Another selected paper, MathCanvas, Intrinsic Visual Chain of Thought, for Multimodal Mathematical Reasoning by Shi and colleagues, enables AI to solve geometry problems by drawing diagrams. The method achieves an 86% improvement over existing multimodal models through two-phase training involving visual manipulation and strategic reasoning. This moves AI from pattern matching toward true understanding of mathematical concepts. The third selected paper, Terra, Explorable Native Three-Dimensional World Model with Point Latents by Huang and colleagues, represents the world in intrinsic three-dimensional space from the outset. Using a point-to-Gaussian variational autoencoder that encodes three-dimensional scenes efficiently, the approach guarantees multi-view consistency in generation. This work provides foundation for robotics simulation and virtual environments. Future directions point toward deeper integration of modalities, including touch, sound, and smell, in specialized applications. Embodied AI will learn through physical interaction rather than passive observation. Environmental sustainability of large models requires more efficient architectures, while safety, reliability, and ethical deployment systems become increasingly critical as these technologies mature. This presentation was synthesized using GPT DeepSeek-chat model with text-to-speech processing via Deepgram. Visual descriptions were generated with StableDiffusion, and human expert review ensured accuracy and coherence. Potential oversights are acknowledged despite comprehensive review processes. Subscribe to AI Frontiers for weekly deep dives into AI research breakthroughs. Our analysis covers hundreds of papers across computer vision and related fields, with expert synthesis of complex technical concepts. Join our community of AI enthusiasts and researchers staying at the forefront of artificial intelligence development. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprint server.